Hello, Algebras. Welcome to your Chapter 9, Lesson 3 notes on multiplying radical expressions. So, just a quick reminder of how to simplify radical expressions. We'll use this example that we've got right here. If you've got a number under the radical that isn't itself a perfect square, but that is evenly divisible by a perfect square, you do have to make sure you pull out that perfect square factor and take its square root. So even though it itself isn't a perfect square, if it has a factor that is a perfect square, even that factor is not allowed to stay under the radical. You have to take its square root. So since 125, the number under the radical right now, is actually divisible by 5, which is a perfect square, what we do is we take radical 125 and we divide it into a perfect square radical and a leftover radical. We take the square root of the perfect square radical, the square root of 25 is 5, and then we're stuck with this radical 5 forever and ever and ever. But these two pieces are multiplied together, so this doesn't need to be here, but 5 radical 5 is our answer here. Well, when we're multiplying radical expressions together, honestly, it's just bigger simplifying problems. You can multiply under the radical. I'm going to skip right down to multiplying single term radicals right here in the middle. When you multiply numbers together under the radical, we get an equivalent answer to if we just had that radical in the first place. But it goes back to simplifying in that if that new result is evenly divisible by a perfect square, then you can't leave that perfect square under the radical. So this is a great example of that. Let's say we've got radical 2 times radical 30. Neither of those are perfect squares, and neither of those have a perfect square factor. But when I multiply radical 2 times radical 30, I get radical 60. Well, 60 is divisible by 4, which is a perfect square. So this answer can't be the end of what I'm doing. I have to pull out that perfect square factor, take its square root, and then see what my leftover is. So my answer here is 2 radical 15 as my final answer. So let's look at a couple of exercises where what we're doing here is not just multiplying the radicals together, but also making sure that our answers are in simplest radical form. So I've got in exercise 2, number 1, I've got radical 2 times radical 8. Now, neither of those are perfect squares. But when I multiply the two numbers together under the radical, I get 2 times 8 is 16. Well, is 16 a perfect square? Yes. What's the square root of 16? It's 4. So this answer doesn't have a radical remaining. Okay, over here on number 2, radical 3 times radical 12. Well, neither of these are perfect squares, but when I multiply the two numbers together under the radical, I get radical 36. Is 36 a perfect square? Yup. What's the square root of 36? It's 6. So far, what's happened when I'm doing this is I'm actually getting answers out that are integer answers, no radical leftovers. And if we think about it, let's just going to use my graphing calculator to prove that this is actually correct, that we are allowed to multiply under the radical together. Let's take radical 2, and then I arrow out here and multiply by radical 8. And what do we get? So we did do that correctly. Okay. Let's keep going and let's look at number 3. Okay, so radical 5 times radical 20. Again, two numbers under the radical, they're multiplying together. Okay, so the answer to them multiplying together stays under the radical. So let's see, 5 times 20, isn't that 100? Oh, is 100 a perfect square? Yes, take its square root. What do we get? 10. Let's do number 4 over here. Now you've got coefficients and radicals. Now the coefficients, they would multiply together. The radicals, the numbers under the radical, the radicands, they would multiply together. So 4 times 3 is 12. The radicals are 15 times 2, which is 30. And we ask ourselves, is 30 a perfect square? Nope. Okay, is 30 evenly divisible by a perfect square? Well, let's try. 30 divided by 4. Okay, that's a no-go. 30 divided by 9. Nope. Okay, 30 divided by 16, my next perfect square. No, and actually I'm kind of coming too close to 30, aren't I? Because now my next perfect square, 30 divided by 25, doesn't work. My next perfect square is 36. So 30 is not evenly divisible by a perfect square. It is simplified already. There's my answer. Let's try 7 radical 12 times radical 8. Now again, 7 is my coefficient. The coefficient in front of radical 8 that's not written in there is actually a 1. It's just not, we don't need to write it in. We have 1 radical 8 present. So 7 times 1 on the outside is 7 as my coefficient. Radical 12 times radical 8 is going to give me radical 96. Okay, now 96 itself is not a perfect square, but it is evenly divisible by a perfect square. Let's find the largest perfect square that 96 is evenly divisible by. We'll start with 4. Okay, so look at that leftover. I know that 24 is still evenly divisible by a perfect square, so that is not the smallest leftover possible. So now let's try 96 divided by 9, the next perfect square, and see if that works. No. Okay. So now 96 divided by 16. There it is. So we still take radical 96 and separate it into perfect square and leftover. We take the square root of the perfect square. Square root of 16 is 4. And now we multiply that 4 times the coefficient that was already out front. 7 times 4 is 28. My leftover is radical 6. So my final answer is 28 radical 6. It is just a larger simplifying question. For number 6, -2 and +6 are on the outside of my radicals. They're my coefficients. They multiply together. They give me -12. My numbers under the radical are radical 3 and radical 6. They multiply together to give me radical 18. Now, is 18 a perfect square? No. Is 18 evenly divisible by a perfect square? Yes. That would be radical 9 and my leftover radical 2. I take the square root of 9, I get 3. I have to multiply that by the coefficient that's already out front, which is -12. -12 times +3 is -36. My leftover radical, radical 2, -36 radical 2 is my final answer. Now, really, this is all I personally expect from you. However, let's look at a few slightly more challenging questions here, just to see if we can get the gist of what's occurring when we're multiplying radicals, okay? So, in exercise 4, number 7, we're looking at distributing a 6 when one of the two numbers in the parentheses has a radical attached. So again, the 6 is outside of the radical. It would multiply by anything else outside of the radical. 6 times -5, that's a -30. No radicals involved there at all. Now 6 times 3 radical 2, the 6 and the 3 can multiply together to give me the 18 attached now to the radical 2 by multiplication. Since 2 is not a perfect square nor divisible by any perfect squares, there is your final answer. 2 separate pieces because they don't both have a radical 2 attached. They can't add and subtract any further. I like 8. I think 8 is interesting. 2 radical 3 times 3, right? So 2 radical 3 times 3, right here. The 2 and the 3 here are outside of the radical. So those multiply together to give me 6 radical 3. The radical 3 didn't multiply by anything because there wasn't any radical to multiply by. Now 2 radical 3 gets multiplied by radical 12. Well, 2 times the number in front of radical 12. That's a 1. So 2 times 1 is 2. Now radical 3 times radical 12. Those are both under the radical, so those multiply together to give me radical 36. Can that simplify? Since 36 is a perfect square, that simplifies further. We take the square root of 36, we multiply it by the coefficient that was already out front. We get 6 radical 3 plus 12. Now, a lot of people like to rewrite that and put the rational number before the irrational number. It doesn't actually matter because they cannot add and subtract. They are not in the same number group, right? They're not in the same number set. 12 is rational. 6 radical 3 is irrational. Leave them separate. They don't both have a radical 3 attached to them. Now, these are really cool. Binomial times binomial. This is a FOIL. I'm only going to do one of these for now, and I'm going to show you another one in the graphing calculator. There'll be a reason. When we FOIL, it's first, so the first 2 multiplied together, we get 6. Outers multiply together. 2 times radical 8 is plus 2 radical 8. Inners, 3 times radical 8 is plus 3 radical 8. And lasts, there's your FOIL, even when it's not necessarily just x's involved, right? Radical 8 times radical 8 is a plus radical 64. Now, there's a couple of things that probably you're thinking about right now, which first thing is radical 64. Isn't that a perfect square? Yes. So we take the square root of 64 and we get 8. Second thing you're probably thinking is, wait a minute, don't I have like radicands here? Can't I just add those up? You sure can. You got a radical 8 and a radical 8. Let's add their coefficients together. So 2 radical 8s plus 3 radical 8s is 5 radical 8s. So I combined these two like terms. This 8 that you took out of the radical 64, that's rational, just like 6 is rational. Those are 2 numbers. Add them up, you get 14. 6 plus 8 is 14. Now here's the problem. Is that radical 8 fully simplified? So we need to simplify radical 8 into radical 4, radical 2, take the square root of 4, you get 2, and we end up as our final answer of 14 plus 10 radical 2. They can't add or subtract any further because they aren't like terms. I'm going to skip 10. Number 11, you should probably see something that we kind of talked about before. When we looked at conjugates, when they FOILed up, you got dots, difference of 2 squares. Well, actually, that's the same thing that happens with radicals. When you FOIL up with conjugates for radicals, you get a perfect square minus a perfect square. And so radical 13 times radical 13 is radical 169. Radical 3 times 4 is plus 4 radical 13, radical 13. Negative 4 times radical 13 is a negative 4 radical 13. And negative 4 times positive 4 is a negative 16 at the end. What do you notice in the middle? Those are opposites of each other. They're like terms that combine to give me 0. Meanwhile, 169 is a perfect square, so the square root of 169 is 13. So 13 minus 16, because the radicals canceled out, is a negative 3. You end up getting an integer answer. Okay, so this is a really cool thing that had happened there. Now, these are all challenges. These I'm not expecting you to be perfect at. I'm also not expecting to ask any of these questions on any assessments, but technically, because you know how to both multiply and add and subtract radicals, you technically could handle these if they were put in front of you, which is why I wanted to make sure you saw those. So, like what happened on number 3, you got an answer, you got a number under the radical that was a perfect square and you took its square root. What happened on number 11, you got 2 integer answers that subtracted, they combined. And so when you actually can take the square root of a perfect square that's under the radical, you have to do it. When you can actually add and subtract integers that are together, you have to do it. Okay? If you have any questions about lesson 3, please do let me know. Please practice and do try the challenge questions. There are a couple challenge questions on the homework for lesson 3. Please give those a try. Ask me questions if you have them. But otherwise, we'll be prepping for a quiz on lessons 1 through 3. Okay? Let me know if you need anything. I'm always here to help, algebras. I'll see you soon. Bye.